All right, we're going to continue talking about the lab experiment 8 and 9, um, which is chapters 11 and 12. And so the next example we're going to look at is N2O. N2O is nitrous oxide. Nitrogen, nitrogen, they say, has very rich redox chemistry because the oxidation state for nitrogen varies from what to what. -3 to +5. So give me a nitrogen in the -3 state. Things like ammonia or amines are going to have nitrogen in the -3 state. At the +5, what do you see for +5? Nitrate. Nitrate has nitrogen in the +5. And then we have a whole bunch in between. For example, N2 has nitrogen in the 0 oxidation state. And then we could look at some others, like NF3. NF3 is going to be what? It's +3. But we have a lot of oxides, etc. And there are a whole bunch of compounds that fill up in between here. As far as the oxides go, we have the NOx, which will have different X values. For example, if X is equal to 1.5, then we form something called nitrous oxide, N2O. Historically, the Aus, comes from the lower oxidation state. So what is the oxidation state of nitrogen and nitrous oxide? Is +1. And then we have something called nitric oxide, which has a higher oxidation state for this. And so nitric oxide would be in +2. So the problem with this is that there are only two, Aus and the ick, convention, like ferrous, ferric. But what happens if there's more oxidation states? Well, if there are more oxidation states, then, for example, nitrogen dioxide, NO2. Well, in NO2, it's +4. And so the nomenclature runs out. So this best, this Aus and the ick convention's old, and it's been replaced by something a little bit more, requires a little bit less memorization. That is, this would be dinitrogen monoxide, this would be nitrogen monoxide, this would be nitrogen dioxide. That's a better nomenclature system, but these are the historic names for these. Anyway, what we want to do is we want to figure out what is the structure of nitrous oxide. Nitrous oxide, people know that because it's also called laughing gas. So let's take a look at what the structure of laughing gas looks like. First thing is we need to total up the electrons. So we got 2 nitrogens, this is going to be 10 electrons, and 1 oxygen is 6 electrons. This gives us 16 electrons. A lot of people like symmetry, so what they do is they do this. And this is no problem because oxygen, oxygen is more electronegative, so you typically don't think of it as a central atom, but oxygen often occurs as a central atom, in between 2 other atoms, because it likes to form 2 bonds, like water. In water, oxygen's the central atom, right? And so this could just be a normal link here that we would expect. But normally what you do is you do put which one goes in the center usually? Which one goes in the center is the less electronegative, and nitrogen is less electronegative. So on the one hand, we have a nitrogen in the center here, which is fine because nitrogen could be a center atom like in ammonia, or nitrogen dioxide. And so either of these could be the central atom. But typically we would go with, if we're pressed for time, which one would you go with? I don't know, because oxygen, well, let's try them both and see. And so if we put oxygen as a central atom, then we fill in the octets for the remaining. And that takes care of 16 electrons there. Except the problem is when you look at this structure, oxygen doesn't have a octet. And so we'll drop in a pair of electrons like this. So we drop in a pair of electrons and form a multiple bond. Oxygen is going to get closer to an octet. But not quite. It's 2 electrons short of an octet. And so what we could do is we could pull the electrons off this nitrogen or pull another pair. So should we go single, triple, or should we go 2 doubles? Let's go two doubles would probably be more, I mean, this seems like it would be more stable, perhaps. Okay, now everybody has an octet. So everybody has an octet. Is everybody happy in this particular structure? If every atom has an octet, are we done? This is it. No, because when we're doing Lewis structures, we always have to check the formal charge. If we don't check the formal charge, then we don't know, how those octets were obtained. And so let's take a look at the formal charges that we've just generated here. And if we look at the formal charge on nitrogen, nitrogen has how many? 1, 2, 3, 4, 5, 6. Nitrogen has 6. It normally has 5. So it gives it a negative formal charge here. And this nitrogen is the same, so it'll have a negative formal charge here. Oxygen is 1, 2, 3, 4. Normally has 6, so it's plus 2. So the way you visualize a formal charge scenario like this is, there's this tug of war for electrons, and who won? Well, this is not a tug of war in the sense of polarity, where you're pulling the electron cloud. This is a tug of war in the struggle for all these electrons. Let's say there's a whole bunch of electrons in a pile. And basically, the atoms go and get all the electrons in the pile. Well, nitrogen ends up with an extra, each nitrogen, and oxygen ends up with 2 short. Now, what do you think in terms of strength? In terms of strength, oxygen has a higher electronegativity. So does this make sense? The oxygen ends up 2 short and each nitrogen gets an extra. Does that look like a stable formal charge to you? No, this looks terribly unstable. Terribly unstable. And also, when you generate formal charges like this, you have to think in terms of charge separation. In terms of moving. We're going to move an electron off oxygen onto nitrogen. When you create separation of charge, this is called a voltage. And creating voltages requires energy, tremendous amounts of energy. And so this formal charges are bad, unstable. Formal charges are unstable. Well, we went for 2 doubles here. But alternatively, what if we went for a single and a triple? Would that improve things? And so let's go for a single and a triple here. And so I'm going to branch off this way and see, if we could have made a more stable structure by going single, triple. All right, everybody has an octet, which is good, but let's take a look at the formal charges and see. In this case, what the formal charges are. And 1, 2, 3, 4, 5, 6, 7. 7 electrons. Nitrogen is supposed to have. This gets a formal charge of -2. 1, 2, 3, 4. This is +2. This is 1, 2, 3, 4, 5. This is 0. How does this formal charge arrangement look like to you? Essentially, oxygen's lost 2 of its valence, and then nitrogen's gained 2 extra electrons for containing the octet in this. Does that look very stable? This looks even worse. This looks worse here because this nitrogen's getting two. And so these high formal charges, you know, and you got to think of it in terms of I1, I2. Each successive loss of an electron doubles the ionization energy, roughly, right? And so this is not looking good here for this. And so, you know, this one looks better than this one, but both look awful. Is there any other alternative? There's no other alternative, and so basically there's other alternatives, but they don't have an octet. Not having an octet is unstable as well. You know. And so it doesn't look good for oxygen in the center. Maybe it's better for nitrogen in the center. And so let's go over here and put nitrogen in the center. Comes out better or not. So we complete the octets to the outside. Actually, oxygen should get its octet completed first. Why? Yeah, I'd probably complete oxygen over nitrogen first because oxygen is more electronegative. But it doesn't matter because there's enough electrons to complete both. But here, the central nitrogen doesn't have an octet. And so in order to make an octet, when we run out of electrons, is to make double bonds or triple bonds. And so who do you think is going to give up the electrons easier, nitrogen or oxygen? Nitrogen. So it just makes sense to make the double bond off nitrogen first. Because oxygen is more electronegative. Hold on to the electrons more tightly. But the central nitrogen still doesn't have an octet. And since it still doesn't have an octet, what can we do? Well, we got to make another bond. And so now this is tricky. Should we take another pair off nitrogen, or should we take it off oxygen? Well, we've already taken one pair off nitrogen, right? So should we take it off nitrogen or should we take it off oxygen? Well, let's see. Maybe formal charge might help us here. So we got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So this has an extra electron, -1. This has an extra electron, -1. Both of these are -1 right now. And so it's hard to say which one we take it off because since we already took it off nitrogen, so we have two choices here. Let's try them. What do you think? Just take it off the oxygen, make it nice and symmetrical, right? Two double bonds. And so let's go ahead and take it off oxygen and see what happens here. So we'll take it off the oxygen, and we end up with nitrogen double bond to a nitrogen double bond to an oxygen. And so this looks nice and symmetrical. Whereas if we took it off this nitrogen, let's take a look at the other scenario here. If we took it off the nitrogen, we'd end up going this route instead. Here. And we end up with a nitrogen triple bond to a nitrogen single bond to an oxygen. And so which of these two structures, both of them have octets, which of these two structures do you like better? Well, first thing we got to do is figure out what the formal charges are. We always got to look at the formal charge when we're doing Lewis structures. And so look at the formal charge here, 1, 2, 3, 4, 5, 6. This nitrogen has an extra. 1, 2, 3, 4. This nitrogen's short. 1, 2, 3, 4, 5, 6. This oxygen's 0. Okay, then we go over here. 1, 2, 3, 4, 5. This nitrogen 0. 1, 2, 3, 4. This nitrogen short 1. 1, 2, 3, 4, 5, 6. This oxygen has an extra 1. This is, you know, what I've been telling you. If there are two nitrogens in the tug of war, which one wins? Well, it looks like. But can you avoid it, a situation like this? Because in order to do an octet, we have to have a formal charge on nitrogen. It's like, otherwise, we can get rid of that formal charge of nitrogen by bringing another pair down. But if we bring another pair down, what's going to happen is, actually, let's try that. Let's see. If we bring another pair of electrons down, actually, let's take it off this, because this is negative, so we'll take it off that nitrogen. Oh, this is looking good. This is looking good because now look at all the formal charges. All the formal charges are 0, 0, and 0. Perfect. Formal charges are 0. Zeros are good because, you know, it's not an ion, so you have an even distribution of electrons, a fair, even distribution of electrons. And so how does this structure look to you? This structure looks particularly bad to me. It looks bad to me because in the valence shell of electron, how many electrons? In the valence shell of nitrogen, how many electrons can it hold? The valence shell of nitrogen is 2s and 2p, so it can hold a maximum of 8 electrons. If we look at an octet, when we count octets, we're looking at the total number of electrons surrounding the nitrogen. We have 2, 4, 6, 8, 10 electrons. And so what we've done is we've filled the valence shell of electron, and we still have 2 extra electrons. Those 2 extra electrons have to go somewhere, and those will go into the 3s orbital. Jumping from 2p to 3s is high jump in energy. Having a high jump in energy means that this is not going to be stable. In other words, this cannot have an expanded octet. Nitrogen cannot expand its octet. In other words, all second period elements cannot expand their octet.